All right. So resistors in a circuit and capacitors in a circuit are going to be almost the same principle, except some things are going to be backwards from what they were for resistors. You guys know what a capacitor is? A capacitor is, can you guys tell me? It could, what do you mean charge a certain amount of electrons? I think the word charge, okay? It can store charge, okay? Yeah, it charges instantly. When we're going to learn that it's not always the case, it doesn't always charge instantly. What is the purpose of a capacitor? Yep. But why would you want to do that? Like, why would you want to do that in a circuit? Okay. You could use it for that. There, yeah. So there are some devices that use it for that. Any other uses for a capacitor in a circuit? Defibrillator. Maybe not so much like where they're located, but why they're used is because they can provide a higher impulse of charge in a shorter amount of time than the current from an outlet. Okay, so an outlet is only going to provide you with a certain amount of charge in a safe quantity, whereas you might need it at a huge burst in time. So a defibrillator, for example, can deliver a huge amount of charge in one moment, but it's just getting electricity from a regular power outlet, right? And the way it does that is that it kind of accumulates the charge and then discharges it all at once. All right. So in this lesson, you should be able to calculate how these capacitors work when you place them together in a circuit. If I have the following two circuits, and I wanted to figure out which one holds the most, which one of these would be the most dangerous, right? Because it would hold more charge. Which one would you try? Which one would you guess? And maybe rationalize your guess. So I have capacitors, three capacitors in series versus three capacitors in parallel. Yeah. Yeah.
And like it releases into C2, so it builds up bigger than.
Okay, so the capacitance might be additive. Okay. Any other guess? What does capacitance depend on? Remember, you guys did a lab on that. Yeah. Yeah. Okay. Rowan? Okay. So could you explain to me if the voltage stays the same? And okay, so I want to build up on what Mark said and what Bronwyn said because they're both going together. So in what Mark said, what determines capacitance or how much charge something holds is only dependent on the capacitor itself, right? And okay, so you have the capacitance, and if you want to increase the amount of charge, you could increase the voltage. And in this case, the voltage is going to drop across each one. And this one, the voltage is going to stay constant. So which one of these is going to therefore hold more charge? Rowan said it. Parallel one, because this one, the charges are all going to add up together, and it's going to come in together to form one megacharge, whereas this one, when you charge it, it's just going to discharge and charge this one, and this one, when it charges, it's going to discharge and charge this one, but it's always going to be the amount of charge that the previous one had. So if you had to like think about it, here is totally disconnected from the circuit, right? There is no connection to the circuit. It's literally like a floating piece of a circuit that's behaving like a circuit because of the electric field, but it's not actually doing anything. It's not getting any external output, really. So whatever charge is going to be on the first one is going to discharge onto the second one, is going to discharge on this one. Whereas these, if they're charged all at Q, and remember, the capacitance is based on only the capacitor itself, right? So each of these are going to have their own specific charges Q. When they come together, their total charge would be, in this example, 3Q. All right. So a couple of important formulas that you need to remember. First one is this one that we saw already. Q is equal to the capacitance times the voltage. The charge of a capacitor. Can you guys see that red? Or should I change color? Change. Q of the capacitor is equal to capacitance of that capacitor multiplied by the voltage across that capacitor. All right? So it's not just the general voltage that we're talking about, because in a circuit, you're going to have maybe multiple voltages, and you might have multiple capacitors, and you want to determine the charge of a single capacitor, then you need to figure out what the voltage is across that one capacitor. Okay? And this would be the energy of a capacitor. We won't be using this too much today, the energy, but it is good to know that there is an amount of potential energy stored in a capacitor. All right, so first we're going to do parallel capacitors. And it's, like I said, it's a way to add the charges together. You want to increase capacitance, you would add them in parallel. And because they're in parallel, it follows Kirchhoff's rule that every parallel branch of a circuit should have the same voltage, right? And so therefore, in this case, you can add up the capacitance because, like I said in that first slide, the charges, they all add up together and they form the total capacitance. Okay? The P here stands for parallel. This is what it looks like. So if I have a 9-volt battery here, okay, now I got to switch photos again. If I have a 9-volt battery here, what would be the voltage across each of these capacitors? 9 volts, because they're in parallel. 9 volts here, 9 volts here, 9 volts here, and 0 volts, 0 volts, 0 volts. And I can now figure out what the charge is on each capacitor as well. Because this one is going to be Q is equal to C times V. This one is going to be Q is equal to C times V. This one is going to be equal to Q is equal to C times V. This is going to be Q1, C1, Q2, C2, and Qn, Cn. Make sense? All right. So a series capacitor can only be charged to the I'll get to it. The charge stored in the first charge is charged by induction. So what I mean by that is, and this is why if I have one capacitor, is that the end of the screen? If I have one capacitor like this, in series with another capacitor, and this capacitance right? It's got, let's say, positive, positive, positive plate, negative, 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 negative plate, right? Where did these negatives here come from? These negatives, where did they come from? Yeah, the polarized plates. You're right, but be more specific. Which plate? What's that? Well, remember that this here is actually not connected to anything, so there's no current really coming into it. Yeah, exactly. So the electrons are actually coming up from here. The electrons are coming up from here, right? Leaving this side. What? What's going to be now this side? That side's going to be positive. And so if this is plus Q, what's going to be this? Yeah, exactly. It's just going to be minus Q. And what's going to be this? Plus Q again. So the charges aren't changing. And this one here, what's it going to be? It's going to be minus Q, right? And I can do this forever and ever and ever. My charge is never going to add up. My charge can't change because it's being charged by induction, right? It's this positive plate here is inducing a charge here, thereby inducing a charge here, thereby inducing a charge there. So all these series of inducted charges well, they're not going to add up. They're just going to be the same all throughout. Okay? So that's why they say here that there's going to be a voltage drop across each capacitor, and the charge is always going to be the same. Notice it's always the same Q, regardless of what the capacitor is. The capacitance 1, capacitance 2, capacitance S. Doesn't matter, right? Because the charge on them, if they're all in series, is going to be the same. And how we add the capacitance up in this case is by doing the opposite of what we did in resistances, right? So in resistors, when they're in parallel, you would do this formula, but now you use this formula when it's in series. You guys see how it's backwards from when it's when you're talking about resistors? You guys see the parallel? See what I did there? Okay, that's pretty much it in terms of theory for capacitors. We can go ahead and do some problems. So in this case, rank in order from largest to smallest the capacitance of these three circuits. Which one's going to have the highest? Which one's going to have the middle one? And which one's going to have the lowest? Yeah. B has the biggest. I'll do it in the blue.
And A and C are equal.
A and C are equal. You're right about B. A is bigger. Why? Exactly. Yeah. So B is greater than A is greater than C. You get that, Mark? All right. Any questions about that? How I got that? All right, here we go. This is basically a resistance circuit. They try to find the equivalent resistance. Here I'm just doing the opposite. Instead of finding the equivalent resistance, I'm asking to find the equivalent capacitance. It's totally the same idea of it, right? You add the series up ones first, and then you add up the ones in parallel, and voila, it's done. So let's go ahead and do that. Which one of these are going to be in series? Or are there any in series? Yeah, absolutely. The 20 and the 5 are in series, so we can add those ones up first. right? And that would be 1 over 20 plus 1 over 5 to the minus 1. That's going to be 5, 20 over 5. That's going to be 4. What are the units? What are they? Microfarads. All right. And now I have, kind of hard to see on, you guys can see it, okay, right? Can you guys see that? The yellow on the white part? So that's going to be a 4 microfarad, oops, not pi, but microfarad capacitor. It's going to be in parallel with the 6 and in parallel with the 20. So now we can add these ones up together. So it'd be 6 microfarads plus 4 microfarads plus 20 microfarads is equal to 30 microfarads. And now I would have I could cross all of these guys out and have a 30 microfarad capacitor there and add those ones in series to get the total capacitance. So 1 over 60 plus 1 over 30 to the minus 1 is going to be 20 microfarad. And this would be the total equivalent capacitance. So we call this CEQ, not REQ. Is good? Any questions? All right, let's do some examples. We'll start off easy. An electric circuit was accidentally constructed using 5 microfarad capacitor instead of the required 15 microfarad value. What can a technician do if they only had 5 microfarad capacitors? How would they have to wire them in order to total capacitance of 15? Yeah. 3 of them in parallel, absolutely. As simple as that. Yeah. You have three capacitors. You want to arrange them in such a way that you have the greatest capacitance. How would you wire them? Parallel. And if you want the least, yeah. Okay. So now I want you guys to do this one. The capacitance of the circuit below and find the charge. We'll do the A alone and we'll do the B together. Okay. you have an answer for A? Total equivalent capacitance? Yep. How much? 20.8? Units? Microfarads. Okay, great. All right, so I have this 20.8 microfarads. This is my CEQ. And now I have to find, okay, so B is going to be a bit more tricky. We need to find the charge on each capacitor. Before I do that, is this, if I had to tell you, ask you what the voltage is at this point, what would you say? 45. Find an imaginary point here. What would it be there? What would the voltage be there? 45. How about here? And here? 0. So that means the voltage across these two is going to be 45. You don't know what the voltage for each one is going to be, but this one is going to have a total voltage of 45 on it. So we can do that one first. So this has a total voltage drop of 45. And the way to calculate charge is, well, it's pretty easy. It's just Q is equal to C times V. So we have, where's this? We have 12.5, but it's not just 12.5, it's 12.5 times 10 to the negative 6, because it's a microfarad. Multiplied by 45 volts, and that's going to give us our charge in coulomb. If you left it in microfarad, you'll get your answer in microcoulomb. We changed it to farad, so we're going to get our answer in coulomb. Did you get an answer? How much? 5.6 to the negative? Okay, 5.6 times 10 to the negative 4 coulombs. Very good. Okay, perfect. We found the charge on C3. Now we got to find the charge on C1 and 2. We know that they're supposed to be equal, right? So what we can do is we could have the equivalent resistance for these two capacitors. And it doesn't really matter because the charge is going to be the same on that equivalent capacitor versus if they were separated individually in series. So we can figure out that if they were together, the CEQ of those two, what would it be? The 8.3, I think? Yeah, so this is the same as one 8.3 capacitor. So I can remove that one, I can remove that one. Then I can do that Q is equal to C times V. That's 8.3 times 10 to the minus 6 times 45 volts. And that's going to be how much? Right. Yeah, no. Yeah. You could do that. Yeah, absolutely. Yeah. Someone have an answer for this? What's the charge on at this capacitor here? 8.3 times 10 to the negative 6 times 45. Negative 4? Coulomb. All right. And since they're in series, you can say that that's the same charge for both of them, for C1 and C2. Yeah, sure. Let's go back. Tell me when to stop. This one? So the charge on, you're absolutely right. No, wait. No, this is the total capacitance, not the charge. The charge on each one is the same, but the capacitance is. Thanks, Michelle. All right. So we've done this, and these are just steps to follow if you're going to solve a more complex problem. So you find the total capacitance, you can find the total charge. This is what Melanie said, like kind of like what we did with current before. Remember, we found the total current and we found one current, and we could subtract it to find it for the other branch. You can totally do that. And then you can find the voltage across the capacitors in series. That's basically what we did in that last problem. For capacitors in series, only the first one is charged from the battery, right? So the battery, what it's going to do is whatever the voltage is here is going to cause a charge here. And based on that first capacitor, it's going to charge the second plate on that first capacitor, which is the same charge as the second plate and so on and so forth, okay? This is the drawing that I drew before. So this is going to be plus Q, minus Q, plus Q, minus Q, plus Q, minus Q. Okay? I want you guys to do this one on your own. Talk it out with your friends, whoever's sitting next to you. Try to solve this one. So B is basically asking for what's the Q total. Do I have an answer for A? Units? Good. William, you have an answer for B? Units? Microcoulomb. You guys do this now and try to find the charge on each capacitor. It's a bit more difficult to find the charge. Take your time on it. Yeah.
Like the battery, can feel like the capacitor.
Yeah.
There's a voltage decrease.
Yes.
All right. Can someone find the charge on C1? Johnny? Yeah, 22.4, absolutely. What would be the next step in order to solve this problem? Once I've found the charge on that first capacitor, what would I do next? Or in fact, what do I need to solve the second part of this? What information do I need here in order to solve the charges on each of these capacitors? I need the voltage, absolutely. So that means I need to find the voltage here in order to subtract it from my 12 volts to get what's left for the parallel part. So how do I find my voltage for the first capacitor? It's 5.6. How did you get that? Exactly. If I were to use Q is equal to C times V and solve for V, I would get how much? 5.4? 5.6? Exactly. All right. So now I have a 6.4 volt drop here and a 6.4 volt drop here. Get 0 volts afterwards. And now I can find each charge individually. What's that? It's always Q is equal to C times V. It's like the Ohm's law equivalent of capacitor circuit. So did you guys calculate the C1, C2, and C3? What did you guys get? Sorry, Q2 and Q3? Did you guys get 12.8 for the first one? Yeah? And for the second one, 9.6 microcoulombs. Very good. I did my 6.4 volts multiplied by my capacitance. And here I did 6.4 volts multiplied by this capacitor. Okay, perfect. One more example. You guys do this one on your own. I'll do it here. You guys check your answers afterwards, okay? You have a hard time seeing? You wear glasses? I've never seen you wear glasses. Or contacts? Oh, really? I noticed. Okay, so, if you were to combine these two, you would have just these two in series, right? So that means this one and this one should have the same charge, and this is the only capacitor, and this would be the only capacitor to have it. So this would have the total charge, and this would have the sum of these two would be the total charge, right? So that means this, whatever you calculated in question A, I think it was, or is it, no, not question B. Yeah, in question B, it asks you what is the total charge, right? It asks you what the total charge is. That would be the same charge as it goes to down, because it's in series with the battery. So you have to remember that the charge doesn't change if you have multiple capacitors in series. Okay, so we found that after we found the 22.4. So now we have the charge Q, we have the capacitance C, and we use this formula, Q is equal to C times V to find V. Okay? And then we found the 6.4 by doing 12.5, 12 minus 5.6. Because 5.6 volts were used up here, and 6.4 volts were left for those two branches. Yep. If you're done, take a break, come back at 10:30, 10:35.
same as the initial
Mm-hmm.
charge, and then we divided it by the amount of coulombs by the voltage drop rate. But if we're here, how do we know? Because basically what I did is I found the charge for the one here,
Okay.
and so I did the overall capacity multiplied by the 15 volts. There's 15 volts out.
Yeah, but it's 15 volts there, but you don't know what the voltage is afterwards.
Yeah, so does that mean that this is the charge and then we do Q over C equals V to find the voltage drop? Did that one?
No, you would just get 15 again. So that's
Are you
not how you
sure?
do it. Yeah.
No, because I didn't plug in this value to plug in the overall.
Oh, I see what you did. Okay, so you did 15 volts times
The
overall,
capacity.
right? To find, okay, yes, and that's the overall charge.
Yeah.
And yeah, that's going to be the charge here.
Yeah.
And
So I divide that by this capacitance to give me the voltage drop?
exactly.
Okay.
We have different numbers though. I'm sorry, you got it? I might have made a
On my
mistake.
calculator, so I'm doing it on my phone. So maybe
So you got 15 times 9. I got the same equivalent resistance as you, equivalent capacitance as you.
yeah, it's your
What did you get?
I'm using the
Okay, maybe I made a mistake. Let me go back. Okay, my total charge is wrong. You got 135, Maria? Yes. Yeah. Yeah.
The same as coming out, right?
Right.
But because it's capacity, does that mean that we can't take the initial charge and replace the final charge because there's some charge to
You
it?
could say that.
You could?
Yep. Yep. This capacitor and this capacitor are the same charge.
root G divided by C. You're right. That's why my answer is not working. Okay, that makes sense. Thank you. Yeah. Uh, I, I marked it in the sense that if you did it, you got 1 out of 1. That's it.
Okay, because I wanted to see if I could get the right.
Sure. Come by. You want to just come by after class? No, I didn't. No, not yet.
Okay, let's get started again. Is it like intensive? Like you do this and all right, so here we come. Last part of circuits. It's not complicated, but it is complicated because there's a lot of little nuances that we're going to have to tease out. Even I'm kind of sketchy with it. I tried my best to learn a couple of examples that were hard to get behind. I was trying to do all this thing. I am calculating around. So we're not going to do those. We'll just skip over those. And we'll do some other topic at the end when we're doing next. Now, have you guys learned about half-life yet? Half-life? What's that? The video game? No, nothing weird. The actual like isotope half-life. Yeah, you guys know that? Okay. So you know how it's an exponential function, and after one half-life, half of whatever is left. Keep that concept in mind because it applies to this topic. It's not going to be called half-life. It's going to be called time, which is just time in this case. And RC circuits, as you might have imagined, the R stands for resistors, the C stands for capacitors. We're doing a resistor capacitor circuit where there's a mixture of the two. And the way they charge and discharge, it used to be that when we just had capacitors wired to a battery, that we would consider the charging process to happen instantaneously. I mean, obviously in reality, it's not instantaneously, but for all practical purposes, it's instantaneous. But now if you put a resistor in front of a capacitor, then the charging of it is not instantaneous, all right? So it happens gradually, similar to how an isotope might degrade, right? Same kind of curves. And then they'll discharge, and then the discharge also doesn't happen instantaneously. It happens over time. And if you actually, we're going to do this next class. Next class is for you guys when? Wednesday? Okay, we're going to come back. We're going to have to come back up here for that. Because what we'll do is we'll actually wire your capacitors to light bulbs, and you'll see that the brightness of the light bulb actually changes as a function of time. It's quite interesting. The basic principle is that you have a capacitor that's initially uncharged, right? And then you plug it into a voltage source and it gradually becomes charged. When it's charged, no more current can flow through it. When it's totally uncharged, it acts as if it were a short wire, okay? So a wire with no resistance. So we're going to practice. This is when a battery is connected, current flows through the capacitor. That's initially, right? And then when the capacitor is fully charged, then no current passes through the capacitor at all, and the circuit changes altogether. Okay, here we are. So here is actually the most simple form of RC circuit. So it's got a voltage source, right? It's got a capacitor, it's got a resistor, in this case it's a light bulb, right? And it's got a switch, all right? The switch is important for this because that determines when we start our timer. Yeah. This would definitely be found in the camera, yeah. Actually, all capacitors in reality are wired with resistance. Yeah. Okay, perfect. So now we have these these two graphs here. I want you to just take the time to look at what the graphs are saying, right? So it's the charge on the capacitor as a function of time. And what you notice is that the charge increases. And what kind of function is that? It's a what? Exponential function, exactly. All right. It's not growing exponentially, it's growing logarithmically, but they're both considered to be exponential functions. And what about the current in the circuit? What's happening to the current? There's a term that you might have learned in half-lives that applies here. The current is, so this is the D. It's what? Diminishing? Okay, sure, but that's not the word I'm looking for. Okay? Yeah. Okay, maybe the fact that it starts with a D is not what gives it away. It's decaying. Do you guys remember that term?
right? So the current is decaying, it's decreasing over time, right? And what did I say about a capacitor that was fully charged? Yeah, there's no current. And look at that. When the capacitor is fully charged, the current is very little, right? So if I were to compare, if this was, let's say, 10 sec, whoops, go back. If this was, let's say, 10 seconds here, then if I looked at, I can't see it here because I have my little thing here. But if I looked at 10 seconds here, my charge is at its maximum and my current is at its minimum. Is everything okay? There is what? Out of the valve here? Okay. I think they're just, it's the pressure. It's not so important. If it starts gushing out, let me know, okay? All right. So we have this idea. Now, does the capacitor ever get fully charged? Sure. It's an asymptote. You guys can see that clearly. What happens to an asymptote? Does it ever reach the value of the asymptote? No, it gets exponentially closer to it, infinitely closer to it each time, but it never actually attains it. So that means that you're never actually fully charged unless you consider it at time is equal to infinity, right? So as the limit of t tends to infinity, the capacitance reaches C max, right? So we can write that here so that the capacity as a function of time and t tends to infinity is going to be equal to C max. And what could you tell me about the current as a function of time when t tends to infinity? What is the current going to be equal to at time is equal to infinity, all the way at the end of time? 0. Yeah. Yeah. Any questions so far? Okay. So here we are. We're going to have to kind of figure out what's happening here. Current flows out of this voltage source, and I want to figure out what's going on with my current initially, and then finally, and then perhaps everywhere in between. All right, so what do we say initially a capacitor is? What's the current initially through a capacitor? Back, initially the current is the opposite. It's very, very high. All right, so now, if in fact it's so high, it's as if there was no resistance whatsoever. So you can pretend that at t equals 0, capacitors don't exist. So where is the current going to go? Right? Where's the current going to go? So I'm here at this junction. Am I going to go left or am I going to go down? Sorry, am I going to go right or am I going to go down? Or both? You're going to go both, right? Because what this is at the beginning is just a regular parallel circuit. So at t equals 0, you can make this drawing. T equals 0, your voltage source is doing this.
This one's got a 50 ohm resistor, and this one's got a 20 ohm resistor. What about at t is equal to infinity? Or it can't really be equal to infinity, but at t is very, very, very large. We call it after a long time. Yeah. So there's going to the capacitors are going to be fully charged, right? There's going to be no current here. So what's the circuit going to look like at t is equal to infinity? Yep. Which resistor or both resistors? Both. So I'm going to remind you that there's no current that passes through here. So this is as if you were to cut the circuit here, right? But this current is still complete, right? So the current, the circuit would just be this. Okay. Okay. So far. So I'm going to write that here at t is equal to infinity, no current through the capacitor. Can you guys try to rationalize a reason why there is no current through the capacitor? Rowan, you want to go try? Yes, absolutely, right? So there's a current going this way, but there's a voltage drop for this capacitor, I'm going to call VC, that's providing a voltage difference equal to the voltage difference of the branch. There's going to be a current going this way and a current going this way, and boom, they collide. They kind of repel each other, but to the point where there is no current anymore at all whatsoever. Okay? And this current is actually a product of this voltage source, right? So this current wouldn't exist, current I here at the top, this current wouldn't exist if this battery weren't there. Okay, so that's the next part of it. Now it's the discharge phase, right? So we've charged it, right? The capacitor that is full, nothing is going to happen. Then what you can do is you can flip a switch, cut this current here, right? Cut this circuit there, and then what's going to happen if I cut that circuit where I put that vertical line? So cut circuit. What happens, Mark? Are going to charge? They're already charged. They're already charged. They're going to discharge. But where are they going to discharge? Not the direction, but through which resistors, through which part of the circuit. Okay, well, there are none, right? So if I cut this, right? If I cut this, then this part of the circuit is no longer a part of my drawing anymore, right? And now there is this. Is there anything pushing back this current? No? Melanie? Absolutely, yeah. So these two capacitors now act like a battery, right? And they're going to provide a current in the opposite direction. So you're gonna get current through these two resistors. Yeah, Rowan. Right here. Yeah. So if I cut this here, this battery is essentially useless because there is no voltage drop across these two nodes. So this by cutting this is basically like removing this entire circuit. Everything there is going to go away if I cut the circuit. Oh yes, love the plug. Okay. So all this is going to get cut away. Did I answer your question? Sorry. Oh, so why doesn't it go like this? Because essentially this circuit is removed. It's gone. So you can imagine that it's not there anymore. And that's the discharge phase of the capacitor. All right. So there's a time is equal to 0 when you start charging, and then there's another time is equal to 0 when you start discharging. Okay. So this is the sequence of events. If you were to follow from the beginning, you turn on the switch, you charge at time is equal to 0. At time is equal to infinity, your capacitor is fully charged. Then you turn off the switch, and that's time equals 0 again. And now another new timer starts, and this is the timer in which you discharge your capacitor. I'm just going to, we'll get to the graphs later on. Yeah, Shine. No, I mean, it's like half-life, right? You never totally decay an atom, right? But you can say like when 99% of it or when 99.99% of it has decayed, you consider it pretty much done. It won't discharge unless there is a, you remove that battery, right? So if, exactly. It won't naturally discharge on its own. Yeah. Say that again? Yeah. Because there was no current to discharge to, right? So there has to be some kind of resistor attached to it. And if you touched it, then you're the ground, and then you get discharged. Okay. So far, so good. I'm not going through this. This is one of Mr. Wakarski's crazy circuits. All right. So here's the relationship between time and charge and time and voltage during the charging phase. Okay, so this is only charging phase. All right. You can see that the charge as a function of time follows this relationship. Okay. And remember how in half-life you had a time, the half-life time. You guys remember that? The half-life time in this case is called RC constant. All right. This is the RC time constant. And it's denoted in these slides by RC, but in a lot of places where you look at it, it's denoted by the symbol tau. And that's what you've also been maybe familiar with when you're talking about half-life. What's that? Tau. T-A-U. T-A-U. Okay? Yeah. Final. I'll explain it. Okay? If I were to graph this relationship, what do you imagine it looking like? Charge as a function of time. What do you think it might look like? You're charging a capacitor. So is the charge going to increase from 0 or decrease until 0? increase. And it's going to increase in this way. And this value here is going to be Q max. And Q max is the final voltage of the capacitor multiplied by the capacitance of the capacitor. So that's C multiplied by V final. You want to find out what's going to be the total charge that's going to end up on this capacitor, you're going to have to use the final voltage on that capacitor. Yeah. No. We'll do an example and it's going to use that principle. Yep, Rowan. Okay, because you're not charged, like at the end, at time is equal to infinity, right? You're going to have this value is going to be what? As the limit tends to infinity, this component of the function, so e to the power of a really, really, really small number, so essentially e to the power of 0 is equal to, sorry, this number. It's going to be e to the really, really high number, e to a negative really, really high number, not RC, because the RC is not a variable. So if time is that really, really high number, it's going to be e to a power of negative a big number, that's going to be what? 0. So this is going to be 0. 1 minus 0 is 1. 1 times c times f is equal to c times f, right? So at its capacity, at the highest point, Q is equal to CV. All right. And if we're talking about the voltage across the capacitor, so that's why it's called VC, voltage is also going to increase because at the beginning, there was it's acting like a bare wire. So it's also going to be doing this, where here it's going to be considered to be V max. If we're talking about voltage as a function of time. Now in this equation, I wrote V battery, but it's not always V battery. It's not always the whatever is in the circuit. It's the voltage drop across the capacitor. That's why I wrote V max here, but this is in fact voltage across the capacitor. Yeah. That's the voltage in the capacitor. Delta V is the voltage in the capacitor. And the V battery would be the voltage across the branch of that capacitor. It'll be more clear in the example. Okay, it says voltage across the capacitor. I'll change it to yellow. V max. It would be because you can consider it V battery, but I don't want you to think that it's just the voltage, the battery that we plugged into the circuit, that it's that voltage. It would be the voltage across that branch of the circuit that we considered it. It'll be more clear when we do an example. I'm having a hard time explaining it because it's not very clear to understand. All right.
So again, at the bottom there, I wrote RC is equal to the time constant. We spoke about that. And that CV is equal to the maximum charge. We also talked about that. And here it is. And essentially, when we're talking about fully charged capacitor, we're talking about 5 time constant. All right. So if the time constant is 3 seconds, all right. So 5 times 3 seconds, 15 seconds would be the practical amount of time to fully charge a capacitor. Because at 5T or 5 tau, we're talking about a 99% of the total voltage is going to be across your capacitor. All right. So it's essentially like half-life. After 5 half-lives, you can pretty much consider that your atom is now decayed totally. Okay. One half-life in atomic terms would be when half of it is decayed. 1 tau in this term is going to be 63%, not 50%. Okay? When the capacitor has reached a fully charged capacity, we call that steady state. So in a problem, we'll say how long until this capacitor reaches steady state. You'll have to calculate tau, multiply that by 5, and you can consider that to be steady state. Okay? It's steady because there's no more current that flows through that capacitor. Yeah, it's a constant depending on the circuit. We're going to do that. Kind of like when we did half-life, the half-life depended on the atom. The tau constant is going to depend on the RC constant. So here it is. Now we're talking about discharge. And the discharge, you ignore you have to remove the battery so that there is no potential difference pushing back the current from the capacitor. And then the capacitor is going to be allowed to discharge back into the circuit, right? And the current is going to start off really high, and it's going to decay as a function of time. And the voltage on the capacitor is going to start off really high, and that's also going to decay as a function of time. Okay? So if you were to now sum this up, what it would look like is if you wanted to determine the, let's say, the charge Q as a function of time, it would be increasing like this because it's getting charged. Then you flick the switch, and it would decay like that. Then if you were to switch it back off again, then it would repeat this cycle. Right? And you have something called like it's kind of like a wave function, right? And that's really good for circuits because look at that, for a decent amount of time, you can have, I mean, it would be the same thing for voltage here. If I were to just change the axis here to voltage, it's the same thing. The voltage and the charge graphs are the same. But if you're talking about the voltage through a circuit, look during how much of this time the voltage is considered to be at its height. That's a pretty significant amount of time, right? And if we're talking about an alternating current, for example, right? I'm getting into a bit more difficult material here. If I'm talking about an alternating current, the voltage of an alternating current goes like this. Goes like this, right? And so if you have a capacitor, why did it erase there? If you have a capacitor at this that's discharging, or sorry, that's charging through this low voltage state, right? Then what you have, if you add the two graphs together, you have a more constant voltage source, right? So if you add these two functions up together, you get a much more constant voltage, so that there's no or very little voltage drops throughout the lifespan of your digital device or whatever it is. Yeah. With DC would just be totally straight, theoretically, right? AC is taking turns going in both directions. So it's, at some points it's going to be dropped, at some points it's going to be high. So if you can put it in sync with the capacitor charging and discharging, then you could create a situation where you have almost always a high voltage, which is what your devices need. Yeah. 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 It would be discharging it into the circuit. And so the circuit voltage would increase while the capacitor's voltage would decrease. All right. Let's keep going. So again, this is the, you would close this switch here, right? And once you close that switch, Bowen, you have a question? The thing about our voltage sources or our batteries is that they provide constant voltage, right? So let's say you plug something into the wall, you would get constant voltage or constant AC voltage. Theoretically, the voltage won't die down. In reality, it does, right? But theoretically, it shouldn't. Yeah. So, okay, so then here we close the switch. We can see it closing, closing. And then once you close it, there is going to be a current that goes through this resistor. And you can see that the charges, here there are 4, here there are 2, so the charges decrease as a function of time. And then eventually, there won't be enough to power whatever it is that's on that current. But if you're, let's say you're using an AC current, all you need to do is power it long enough until the next positive wave comes in, and then you can use that time to charge up again. And then once that wave goes down, you discharge again. So you always have this kind of constant voltage source. And for discharging, the equations are very similar, right? You have the, if I were to graph it, can you guys see that color? Yeah, it's not bad. If you were to graph it, the initial charge would be Q max, and then it would die off as a function of time. And again, RC is the time constant tau. And the current provided by the capacitor is also decaying. Have you guys ever heard of something called the UPS, not the United Postal Service, but UPS, an uninterrupted power supply? Yeah, so a lot of like really expensive electronic devices will use something called an uninterrupted power supply because they can't handle voltage drops, right? When there's a voltage drop, their devices become uncalibrated. So like these are, we're talking about like supercomputers. Even some people at home, they're paranoid that their computers are going to get fried, so they'll buy something called a UPS. And what that is it takes into account for the natural voltage drops that we get from Hydro-Quebec by charging a capacitor and discharging that capacitor into your computer, into your device while there is a low voltage, right? Most devices don't need that because the oscillations happen frequently enough that your devices don't recognize it. And there are also capacitors in your computers. But like I said, some things are much more sensitive and require this thing called an uninterrupted. So what you're doing is you're not allowing the voltage drop to go too low for it to harm your device. Okay, so here, this is important. We're going to read this part together. This is kind of like the
the gist of everything, okay? So an empty capacitor acts like a closed switch or like a bare wire with zero resistance, okay? And to find the initial values of the current and the voltage in an RC circuit, you got to redraw that circuit without the capacitors present and a bare wire in its place, all right? So find the current and the potential differences in the redrawn circuit. The charge in the capacitor is zero. The potential difference across the capacitor is zero. Okay, this is going to be how we're going to solve those problems. You need to remember everything that's in this little paragraph. Okay? I would put a star on this page because it really does help in solving a lot of these problems. A fully charged capacitor will shut off current to the branch that it is located on. For that particular branch, there will be no current flow at all, and all the potential difference across the branch is found across the capacitor. And you can use Q is equal to CV to get the maximum charge on that capacitor. All right. It's asking you in this problem here to find the current flowing through each resistor as soon as the switch is closed. So as soon as the switch is closed, what can you tell me about the capacitor? Yeah. This charge will start to gain. What can you tell me about the current flow through the capacitor? Is it full or zero? Or an empty capacitor, what does it act like? If I were to go back and if I were to just go, sorry, not go back, but read up here, what does it say when the capacitor is totally discharged? Exactly, it acts like a closed switch. So you can, for all intents and purposes, draw a straight line there, right? And then find the current passing through each resistor as if it were just a regular resistor circuit, right? So I'd have to find REQ. REQ is equal to 3 ohms to the power of minus 1 plus 12 ohms to the power of minus 1, all that to the minus 1. So it'd be 12 over 5, is that 5.2.2? And if 2.2 is my total resistance, I can find my total current. So 24 volts divided by 2.2 ohms is going to give me something like maybe 10 amps. Can you guys just check that out? Is that the REQ? Did I calculate that right? Because these two are in parallel. These two resistors are in parallel. So you add them, you find the REQ doing 1 over 3 plus 1 over 12. Maybe I made a mistake in my calculation. Is how much? 2.4? Okay. All right, great. So we have 2.4. So that means the current is going to be 10 amps coming out of the battery. Now we can figure out what the current is going through each one. So we know that the voltage drop across each resistor has to be 24. If the voltage drop is 24 and our resistance is 3, so here you're going to get 8 amps, and then by default here you're going to have 2 amps. No, you're right. You don't need a total current. It's a good way to check your work though, because these two numbers should add up to your total. It's okay? All right, now a matter of calculating that time constant tau. Tau is equal to RC. And that's literally R times C. Okay? So it's going to be equal to resistance in ohms multiplied by capacitance in farad. What are the units of RC? Ohms farad, you're right, but ohms farad, it could be simplified. So resistance, if we use Ohm's law, is going to be, so resistance is equal to V divided by I, so volts over amps. And capacitors is equal to coulombs divided by volts. And volts cancel each other out. So you have coulombs per amps. And what is an amp again? Charges per second, so coulombs per second. So the coulombs cancel out, and this is divided by seconds, so it goes up at top. So the units for RC are actually seconds, and that makes sense, right? It's the amount of time for 63% of the charge to be discharged, for example. All right, so now we can figure out what the RC constant is for each of these two circuits. In this case, RC would be equal to 1.0 times 10 to the minus 6 multiplied by 1,000. And this would be equal to 1.0 times 10 to the minus 3 seconds. Yeah. Oh, you're right. It is 2,000. Sorry. 2,000. I don't know if I did my math correctly. Just check it, please. I have the right number of exponents. If I were to ask you, how long would it take for 99% of my capacitor to discharge on my first circuit, what would you do? Divided by 5, Melanie? Multiply it by 5, right? So after one time constant, 63% of it is depleted. After 5 time constants, you consider that 99% of your capacitor is discharged. Okay, so it'd be 5 times whatever my RC value. Okay? Let's do RC here. You guys do it.
got 2.0 times 10 to the negative 3. Is that correct? Yeah. Now, using different valued capacitors and different valued resistances, we can customize the amount of time that we want to fully discharge and charge a capacitor. So windshield wipers do this, okay? You want to make it go fast, then would you decrease or increase the discharge and charge time? Because what you're doing is you're charging a capacitor and you're going to discharge it into the motor of the windshield wipers. You want it to go fast, you want it to discharge more quickly, right? So that you can charge it more quickly, right? So you'll decrease the RC, right? If you want a fast moving windshield wipers, right? And you would increase the RC if you wanted to go slow. Your watches, modern watches, they work on this. A lot of them say they work on quartz decay. So those ones are special because they work on quartz decay. But actual regular digital watches, what they do is they work on charging and discharging of capacitors. So they set it up so that a capacitor charges and discharges within a specific set amount of time. And that's going to determine when the next number shows up for your watch. Okay? So far, so good? It's been a long class. We'll do this example. I'll let you guys out a bit early because it's been brutal. 2 hours of me talking, I don't imagine there are worse things. All right, we'll do this example. We have a very simple kind of capacitor. Okay? Actually, wait, just before I do this example, let's go back one slide. There's one thing I wanted to talk to you guys about. Is this discharge word here, okay? So the RC constant of a circuit can change based on if you're doing a charge or a discharge, okay? So don't think that the same RC can be used for charging and discharging a capacitor, right? It's going to be different. And I have an example. If I go back here to one of my earlier examples, maybe this one. Let's do this one, right? Yeah, Melanie? It will depend on the configuration of the circuit. Yeah. So here, the setup to get to how you would charge these two capacitors, right? Your RC to calculate charging of this would be different because the resistances here are set up in parallel, right? So your R components of your RC calculation are going to take into account these two in parallel. But if I were to cut this, like I said I did, to discharge it, so if I were to cut this part of the circuit to discharge it, now all of a sudden, these two resistors are in series. So when I'm calculating the RC, I have to consider that these two resistors are in series. It was important in that question that we were just doing, that it's asking you for the time constant for the discharge of the capacitor. Okay? It's not always the case, but sometimes it is. All right, so let's read this. The switch in figure beside this here, P2344, has been positioned in the A position for a long time. So what's happening if you position it in that A position for a long time? What does that mean? Yeah, the capacitor is fully charged, all right? Perfect. And then it is changed to position B, and that's when we start our timer. So what's going to happen once you flick it to position B? Discharge, exactly. So the current's going to go flow through the resistor, all right? And there's going to be a current. And it's asking you what is going to be the current immediately after the switch is closed, and then at 50 seconds, and at 50 microseconds, and then again at 200 microseconds. All right. So what we need to do is find. I mean, we need to find everything, right? So we need to find I as a function of time
is going to decay, so we need to know our I max multiplied by e to the power of negative time, and time is what we're going to plug in. So either 0 if it's initial time, or 20 microseconds if it's at 20 microseconds, or 200 microseconds if it's at 200 microseconds, divided by our time constant tau. William, you picked the worst time to not be in class. That was literally the hardest thing we would have done all year, is that. You'll get up, I'm sure you will. So RC is our time constant for this, and this is for discharging or for charging? Discharging, absolutely. So we're going to do 50 ohms multiplied by our capacitance, which is 2.0 times 10 to the minus 6. So 1.0 times 10 to the minus 4 seconds is my time constant. When my capacitor is fully charged, what's the voltage on my capacitor? When it's fully charged, 9 volts. So my V is 9 volts. My V on my capacitor is 9 volts. My resistance is 50. So I can find my max current, because I'm going to have my max voltage. And this is, Shawnee, before you ask me what does that VF mean, this is that VF, right? So this is after it was fully charged. That is now yeah, you can, whatever you want to call it. So I can figure this out. 9 divided by 50. What is that? I can't do that in my head. 18? 0.18? 0.18? That's going to be my total current. And now I can plug everything in into my equation. I have my current at time t, which is what I'm solving for. Well, this is this is going to be my current at time equals 0. So actually, I don't need to calculate anything else, right? That's my total current. When my voltage is at its max, or it's at my after charged voltage, then that's going to be my current, and that's going to be my current at time equals 0. But if I wanted to find it at 50 microseconds, then I would have to do I max, which is 0.18 amps, multiplied by E to the power of minus 50 times 10 to the minus 6, divided by my RC, which is, where is my RC? 1 times 10 to the minus 4. And that would give me my current at time equals 50 microseconds. Yeah, it's the time that is asking you, that's your T, and your tau is your RC that you calculated. So it's T over tau, time over time. What's that? Do I have two variables? It is that. It's e to the power of 50 microseconds divided by, is that 100 microseconds? What's that? The t is this.
Can someone give me an answer? 1.65. It should be less than 0.18, ideally. How much? 0.11. Units? Amps. Could you guys, I'm not going to do 200 microseconds because it's just a matter of plugging in another number. But I want to ask you guys a question about my circuit. When I charged it, was it an RC circuit? It wasn't, right? Because there is no resistance involved when my switch is at position A. But you can still calculate using RC to determine how long it takes to charge. Let's figure that out. What would be my time constant if I didn't have a resistor? Well, my resistance is 0 ohms multiplied by my capacitance, which is going to be equal to 0 seconds. So how fast is it charged? Instantaneously. All right. In reality, your wires will have some internal resistance, so you will take some time to charge your capacitor, right? But theoretically, if your wires are totally free of any type of internal resistance, your capacitor charges like that. Okay, and you calculate it because your RC value is actually just 0 seconds. To the power. So something as e to the power of something divided by 0. Or now that you've done calculus, you know that nothing's ever divided by 0. It's always as it tends to 0. So you have a very big number. So e to the power of a negative, very big number. So essentially 0. So you're always going to be at 1 minus 0 or 0. That was intense. I'm sorry about that. I promise I'll give you guys time in class next time on Wednesday to practice these problems. We'll do the quiz. I'll give you guys, what's a good time? 40 minutes? 40 minutes? It's going to be two circuits that you guys are going to have to solve. One Wheatstone, one loop circuit. Yeah, so let's say 40 minutes, and then after that we'll practice some of this stuff. Have a great weekend. Thank you, guys. Yeah. Let me think about it. Maybe what I can do is, after everyone's done, I'll dismiss everyone and you can have a few more minutes to do any other station. Okay. Does that work? Bye. Have a good weekend.